All right, in this example, let's say we're considering the ellipse x squared over 16 plus y squared over 9 is equal to 1. Well, again, for ellipses, we see it's an addition. That's what tells us it's an ellipse. The larger number is under the x squared, so A is 4 because 16 is 4 squared. That's where these 4's come from. B is 3 because the square root of 9 is 3, or 9 is 3 squared. And that's where the those distances of 3 come from. So we know that's the graph, and just by inspection, by looking at this, we can see the domain is -4 to 4. But let's just show this analytically, by hand, that it really is. So in other words, let's solve this equation for y squared. So if I subtract x squared over 16 from both sides, I get this. Multiply both sides by 9, I get 9 times the quantity, 1 minus x squared over 16. Then I take the square root, so y is equal to plus and minus, the square root of 9 is 3, and here we have the square root of 1 minus x squared over 16. Well, for square roots, we know to find the domain, whatever the radicand, whatever under the square root, that's got to be greater than or equal to 0. So 1 minus x squared over 16 has to be greater than or equal to 0. If I multiply both sides of this equation by 16, I get 16 minus x squared is greater than or equal to 0. If I graph this, y equals 16 minus x squared, well, we know that's an upside down parabola because of the negative, and it's going to go up to 16. And if I factor this, 4 minus x, 4 plus x, we know this is equal to 0 when x is 4 and -4. So those are the x-intercepts. And by looking at this, we can see the graph is above the x-axis. It's positive. Our y values are positive above the x-axis. Between -4 and 4, that's where our graph is above. That's what we would expect because we could see that from our graph.